Then we have two comprehensive calculations. Okay. So for the first problem, a block is a very typical problem. A block slides along an inclined plane, and it's a frictional inclined plane. Okay. So you have inclined plane, a block with mass 10 kilogram, slides down. The angle is 36.9 degrees, and the height is 6 meters. The block, okay, the coefficient of the friction, mu k equals to 0.2. Okay. There are many different ways to do the same problem. Okay. You can use total energy conservation. You can use the work kinetic energy theorem. Some of you even try to do this in a very standard way. Okay, if you go back to think about force analysis, you can try to find out the acceleration. With the acceleration, you can use some the kinematic equation to find the velocity here, right? Okay, so there are many different ways. You can use work kinetic energy theorem, you can use the total energy conservation, you can even use the kinetic equation. So here I will use total energy conservation to solve this problem. Okay, so of course you cannot use mechanical energy conservation. Okay, so one of the common mistakes is that many of you try to use, not many, some of you try to use K plus U equals to K naught plus U naught. This is wrong. Okay, these two will not be the same as each other because you have frictional force. This is a frictional surface. Okay, so actually you need to add the contribution from the frictional force. So what you cannot use this. What you can do is the work kinetic and the total energy conservation says that the kinetic energy, the mechanical energy change in this case is not zero. It equals to the work done by the non-conservative force. Okay? So, in other words, it's final K plus U subtract the initial K naught K plus U. Okay, it will not be zero. In principle, it equals to the work done by the frictional force plus the work done by the normal force F. Okay, but there are many zero terms here. So the work done by the normal force equals to zero. Okay, because it's perpendicular to the motion. And the final mechanical energy, my final potential energy can be set as zero. Okay, if you set zero height at the bottom. And the initial kinetic energy equals to zero, right? It's released from rest. So finally, you get K minus U naught equals to WF. So K is 1/2 mv squared. So it will give you the final velocity. We want to find this one, right? Initial mechanical energy is mg y naught. This is y naught, so it's known. And equals to WF, the work done by the frictional force. So, okay, so usually you have no problem with this side, but okay, there are many mistakes you may make for calculating the work done by the frictional force. Okay, so the work done by the frictional force, WF equals to negative Fk multiplied by T. Okay, and okay, usually you know that can be written as negative mu K normal force N multiplied by T. Okay, so most of you have no problem to write it in this way. Okay, mu K is given 0.2, but you need to pay attention to the calculation of normal force N and distance D. Okay, this normal force is not mg, right? It's not a horizontal surface. It's not mg. And again, this D is not 6 meters. Okay, but so that's a two common mistake you may do. So what is the right expression for normal force? In fact, you need to do the decomposition. This is a wedge. This is a normal force. So if you decompose the wedge, you get Wy equals to mg multiplied by cosine theta, right? So in this case, normal force N equals to Wy equals to mg multiplied by cosine theta. Okay? So this is normal force. And here, how can I calculate D? It's from the geometry here. This one is 6 meters. Okay? Why not 6 meters? And D is this distance. It's a hypotenuse. Okay. So in this case, it will be 6 over sine theta. Right? Okay, that's the distance. Okay. So if you substitute these things into the equation, so WF actually equals to negative mu k mg cosine theta multiplied by 6 over sine theta. Okay. So if you put it here, and then you can calculate the final velocity v. Okay? So you can see here, for this problem, several things you need to pay attention. First, it's a total energy conservation. It's not mechanical energy conservation. So you have this term WF. And second, to calculate the WF, you need to know that in this case, normal force and distance, okay, they are not directly given then, so you have to do some manipulation to find out the correct expression for normal force and the distance. Now, let's look at problem 2. It says that first you have a block 1 with M1 equals to 2 kilogram. It will slide from rest along a frictionless rack from a height of 2.5 meter. Okay. V naught equals to 0. It will slide down here. Okay. And then this block will collide with some rest block M2 equals to 3 kilogram. Okay, this is M1 equals to 2 kilogram. Okay, after the collision, the two blocks stick together. Okay, M1 plus M2, they stick together and it will acquire some velocity, let's say it's U, okay? And this one is V2 equals to 0. This is V1, okay? It's not known, but you should be able to calculate from the first part. That's the second process. There are 3 processes. The third process is that the total block, okay, will go to a region with a coefficient of kinetic friction mu k. So it will slow down and finally stop due to the frictional force. Okay, we know that the stopping distance is 3.5 meters. So it's we want to find mu k equals to 1. Okay. So this problem, you should be able to find out that there are 3 processes. Okay, 1, 2, 3. So each of them, you can use some equation to find out. So from the first part, you have, is it a frictionless thread? Yes, this is frictionless thread. So you can use the mechanical energy conservation for this part. Okay, so the first equation is K naught plus U naught equals to K plus U, right? And K naught equals to 0. Final U equals to 0. So you get mg y naught equals to 1/2 m1 gy naught equals to 1/2 m1 v1 squared. If the velocity here is v1, so this is y naught. So you can find out v1, right? Okay. What is the value for v1?
7.
It's around 7. Okay. So you can calculate it's around 7 meters per second. And once you have the v1, second process is just a collision process. And that's the most simple collision process, completely inelastic. So they stick together after that. So you get m1, the second equation is m1 plus v1 plus m2 v2, which equals to 0. So this is this way. Equals to m1 plus m2, let's call this final velocity vf, okay, after collision, multiplied by vf. Again, so of course with this v1, you can calculate, so it will give you what's final velocity vf? What's that? 2.8 meter per second, right? So that's the velocity here. And the next process, what happens is that you have the total block with some velocity 2.8. Okay, it will slow down and stopped by the frictional force. So the last equation is you can either use the total energy conservation or work kinetic energy theory, right? So if you use work kinetic energy theorem, it will be delta K equals to W net. In this case, only one force is doing work, the frictional force. So that means final K subtract initial K equals to work done by the frictional force, right? Final K is 0, it stopped. Initial K naught, initial K is 1/2 m, this one Vf squared, okay, because this is Vf. And the work equals to negative Fk d, right? And in this, Fk is simple, it's negative mu k mg. Normal force in this case is mg. So it's just negative mu k mg multiplied by d. Is d given? Yes, given. So you get negative mu k mg. So with this equation, you can find out mu k, right? Solve this equation, you can get mu k. Okay? So this problem, you should be able to divide the whole process into 3 parts. The sliding down part, mechanical energy conservation, and followed by a collision process, momentum conservation. Finally, the stopping process, total energy conservation or work kinetic energy theory. Okay, 3 equations here. 1, 2, 3. Any question here? You cannot solve the problem by considering the whole process here. The reason is that you have some collision here. This collision will destroy any kind of energy relationship you may have. So you have to separate.